Go on. Okay. Okay, good. Let me. So in my last lecture, I did something which was not right. So let me correct that first. Okay. Huh? So it was, in essence, what I was saying was correct, but there was one minor thing which I overlooked. Okay. So remember when we did these mappings of f of z equal to log z, right? Then this was equal to log r plus I theta, right? If z is in r e power I theta, r is the magnitude, the length of the this, modulus, okay, and theta is the angle, like the argument of z. Huh? So remember I told you that in z plane, I told you that the circles in z plane, right, get mapped to what? Lines like this. And this is because I am taking argument from 0 to 2 pi, so I will be able to only cover the region where the imaginary part is up to 2 pi, because this imaginary part is exactly this theta. Okay? And circles with mods are bigger than 1 get mapped here as lines, vertical lines. Okay? And circles with mods are less than 1, so if you assume that this is a circle of unit radius, so it is e power I theta, every point here just has mods at 1. Okay? And the circles with basically inside get mapped this way. So this was all fine. But then I considered, what about a line, right? Okay? And I drew a line completely like this. Okay? And I said when you fix theta, but we were actually not fixing angle, we were fixing the argument. Right? So the argument this way is theta, right? The argument of these complex numbers is theta, but the argument of these complex numbers is not theta, it is theta plus pi, right?
Yes.
Huh? So I told you yesterday that this line will get mapped to a horizontal line, right? So this line here will get mapped to a horizontal line, which is not quite right. Okay? So this horizontal line, what would be the height of this line? At theta, right? Whatever theta you are fixing here. If it was pi, if it was, let's say, pi by 3, then this will be at pi by 3. Right? But that's not entirely true, because this part of the line has a different argument, right? It has the line which lies in the part of the line which lies in the third quadrant, right? Okay? It has an argument of pi plus theta, right? So this part of the line will still get mapped to a horizontal line, but somewhere else, not here, right? Pi plus theta, so somewhere above it, right? So whatever statements I made were for this part of the line, right? The one statement that I made was the part inside the unit circle will get mapped to this guy. So it will be from this point to this point, not the one that I displaced yesterday. Okay, good. I will come back to conformal mappings. So this was one error that I wanted to correct. I will come back to conformal mappings, okay? But before that, I want to do what did you do for real functions after learning differentiation? What did you do? After learning differentiation of real functions, right? What did you do after that? Integration. So I want to learn how to integrate complex functions. Okay? Huh?
Yes.
Okay. That's what we'll do today. At least we won't be able to do it entirely today, but we'll start. Okay. How do I do it? Okay. Now having that out of the way, let's start. Okay. Now, how do you integrate real functions? You integrate real functions f from x1 to x2, some limits. Then you put dx f of x. Right? Which is essentially what? Sum. You're summing numbers. Right? You're summing from x1 to x2, sum f of x. Obviously there is subtlety involved. Right? So you have to take, this is a sum, but you have to take some limit. Right? You have to dump infinitely many points between x1 and x2. Okay? With a measure which is dx, okay, and then this thing becomes, finite. This gives a finite answer, okay. Well, not always, but when it has a finite answer, it gives you a finite answer, okay. Now, in the same spirit, okay, I consider integrate z1 consider this. Okay? So I'm asking you that from Z1 to Z2, integrate this complex function. Okay? So what does it mean graphically? So graphically it means that take Z1 and take Z2, integrate f of z, right? But that's not that does not make sense, right? Because you have to ask me that which path should I take to integrate, right? Is it this one? Or is it one which goes straight? Okay? Or is it one which is like this? Which one? Which one are you talking about? So this is not really precise. Huh? Okay? Well, it would be precise if this path didn't matter. Right? If this path, if it didn't matter which way you reach from here to there. Right? If that didn't matter, then yes, okay, fine, this is okay. Right? You can probably do this integral. We'll learn how to do this integral. Huh? Okay. So what my task would be, what my goal is here, okay, to show that this is indeed precise as long as the function is analytic. Okay? That means I have to show that it is what? Path independent. It doesn't matter what complex numbers you are computing f of z on. As long as you are going between z1 to z2, the integration is same. It doesn't matter what path you take. Okay? Now, to show that, let me consider two paths from z1 to z2. So let's keep a pin on that. Let me consider one path like this, okay? And let me call this path as P1, whatever this path is. Okay? And I am integrating going from Z1 to Z2. Okay? And some other path. Okay? P2. Okay? Yes. So I am considering two paths. So what is my goal? To show that the integration here and the integration here is the same. So this is more precise. So integral P1 dz f of z, where P1 starts from Z1 and ends with Z2 through via this, right? Is the same as, this is my goal, integral P2 dz f of z, where P2 starts from Z1 and Z2, but let's take some other path. Okay? Only then the thing that I wrote, integral Z1 to Z2 dz f of z, which didn't have any path, would make sense. Would have some definite answer. Okay? But then I can take this here. What do I get? So let me call this IP1. So IP1 minus IP2 should be what? 0. This is what I have to show. Okay? But minus IP2 is just going in reverse, right? Right? So this path, right? Why is minus IP2 just taking the same path but in reverse? Yeah, exactly. dz. You're just changing limits. So dz would be negative of the dz of this path is this way, and the dz on the other path is opposite. Right? dz, you should think of dz as, see, z is x plus iy, right? So change in z is just dx plus I dy. Right? I is a constant. Right? I is a constant. I square is minus 1. It's a constant. So dz this way and dz that way are negatives of each other. That makes these integrals negatives of each other. Okay? So all I have to say, so basically I have to show IP1 plus I of minus, okay, instead of minus let me just do P3. Where P3 is what? It goes from Z2 to Z1 via this path. Okay? Equal to 0. Right? Now, I'm integrating, I'm starting from Z1, integrating to Z2 via P1. Okay? And then I am integrating over P3, which is just P2 reverse. What does that mean? I am integrating over a closed loop. Okay? simple closed loop. Okay. Okay. They could be a bit more complicated loops, but we'll consider loops like this, like simple loops. Okay. Huh? There's a way to define simple loops more precisely, but let's just stick to what our intuition tells us. Right? Okay, so that means I have shown that integral of this function over a loop is 0. Right? I'll show that that is indeed 0, okay, as long as the function is analytic. See our equations word. Okay? Okay?
Yes, sir.
So basically, I have to integrate a function over this loop. So let me call this loop as C, this whole loop. Right? C is basically P1 plus P3, whatever. dz f of z. I have to compute this. Okay? Huh? But I don't know how to compute this, right? But I know how to do real integrals, right? Real functions or whatever. Okay? Huh? Those things I know. So I just replace dz like this. Okay? And f also I can break down into real and imaginary parts. Okay? And then I do real part separately and imaginary part separately. Okay? That is something I am well versed in doing. Right? We have been doing that. Huh? Okay. So this is integral dx. dz is dx plus I dy. Okay? And f of z is u of x comma y plus I u. Is this fine? So I can multiply, right? Huh? I can multiply. So what do I get? Integral over the closed loop. Right? What do I get for the real stuff? I get u dx. I will drop the x y dependence. Okay. Minus what? v dy. Plus what do I get? Things with iota. In the imaginary part, what do I get? U dy, I get u dy plus v dx. Excellent. Okay. Huh? Fine. Have you ever seen this? Huh? Have you ever seen this? Integral something dx minus some other thing times. Yeah? Exactly. It's Green's theorem, right? Green's theorem. So what is Green's theorem? That if you have an integral like this, integral m dx and dy, what is this equal to? Yeah? It's an integral over what? Huh? Huh? First, what is this integral over? M dx and dy. What is this? What are you integrating over? Loop. Over some loop. Okay. Over some loop. C. Okay. Then what do we get here?
Double integral.
Yeah, double integral dx dy. Partial what?
Partial n by partial x.
Partial n by partial x.
Minus partial.
So basically nx minus
ny.
nx minus ny. Excellent. Okay. So this is the statement of Green's theorem. Okay. Huh? Okay. Yes. Now, but what is this integral over? So now this is what? A double integral. So this integration should be over some area. Excellent. What is that area? No. What is that area? Area of the loop that you are considering. Right? So you have whatever C you have, right? So this integral, this guy, is over this loop. Okay? Huh? But this integral is a double integral, so it has to be over some region, and the region is this. The region inside. Okay? So you have to integrate every point over every point inside the region. What? This scalar function. This scalar field. Right? This would be n is a function of x and y. M is a function of x and y. So this would finally be a function of x and y, whatever complicated way appears right now. Right? So you have to integrate that function, that scalar field over the region. Right? Remember you did those things. Right? Okay, good, excellent. So now let's apply that here because it's the same, right?
Yes.
Right? Okay. So what do I get? Okay. Maybe I can just erase this a bit so that I can focus on that. So what do I get? Make sure there is a minus sign here, so be careful. curtailing this. What do I get?
dx.
First integral dx dy over the region over R, where R is what region? The region bounded by my closed loop. So basically this region, right? This region. Huh? Right? And what do I get?
Minus
Minus Vy, right? Vx. Vx. The one with the dy has to be differentiated with what? X.
yes.
And this one? This is
minus
dy minus Vy plus iota integral over closed loop. What do I get? The one with the x.
Vx dx
Vx. So first this one you take, u x minus v. Right, first this one, dy one comes first. Minus v y. Right, once again dx. Excellent. Okay? And this for what? For this region. For every point inside the region you have to like sum. Right? Okay. Now, but what are we dealing with? Analytic functions. Right?
Yes.
They satisfy what? Cauchy-Riemann. Okay? So can you use Cauchy-Riemann equation?
Yes.
So what is Vx as per Cauchy-Riemann?
It's minus
Huh? Vx is minus u1, right? So this has to zero. Excellent. So this thing, what is ux? What is
Vy.
v1. So this is also zero. Both of them are zero. Right? So what is this again?
Zero.
So zero. Huh? But this has to be zero at every point inside because you're integrating where? Yeah, the v is zero. Right? So we have when we put this integral to be zero, we have assumed that we checked at every point ux and vy, and they are as per they hold Cauchy-Riemann, right? So every point inside this curve, right? Okay, the function has to be what? Analytic. They have to satisfy Cauchy-Riemann equation. Once again, I've been telling this. I will qualify this further. Okay, because there is one more implicit assumption that we have made, that these ux and vy, these are very well behaved stuff, right? They can blow up, right? Then things won't be analytic. Okay, but for now we just ignore that side. We'll come back to it later. Okay, so we're dealing with analytic functions. It means they are good, well behaved functions. They are finite and well defined. The ux, vy, the function itself. Okay, these things were implicitly assumed. Okay, and above all, for the function to be analytic, it has to satisfy Cauchy-Riemann after satisfying all this. So what do we get? Integral c is what? Zero. Right? Which was the aim, right? So coming back, so my integral from z1 to z2 is basically what? Path independent. It doesn't matter what path do I take. Okay? It doesn't matter what path I take. Okay? So this thing now has a well defined answer. z1 to z2 dz f of z. Even though I don't give you the path, this still has a well defined answer. Right? As long as the function is analytic. Okay? We'll put non-analytic stuff slowly. Okay? For now, let's just deal with analytic stuff. So if this is analytic, okay, then this has a well-defined answer. And how do you do it? Just like scalar. So if you want to do, let's say 1 to iota dz z, okay, how do you do? If it is a scalar field, if it was a scalar, sorry, not a scalar, if it was a real function, how do you do? Yeah, exactly. Z square by 2, and then you put limits 1 to iota. What does it give? 1 by 2. Iota square is what?
Minus 1 by 2. Minus 1, sorry, minus 1
Plus 1. So this is 0. This integral is 0. Right? But remember, when can you do it?
When this is
Analytic. Is that analytic? Yeah, it's indeed analytic. So there is no point on the complex plane where z is and Z blows up, Z gives weird answers, Z is well behaved, this, and above all, it satisfies Cauchy-Riemann equations. Right? How was I able to say that it satisfies Cauchy-Riemann equations? Because there is no Z star.
Yes, sir.
Right?
Free from
Z star, this function. Okay? Huh? Is that clear?
Yes.
Huh? Right? Similarly, you can do other stuff. For example, integral 1 plus I to 2 plus I dz, let's say z square. Okay? How do you do it? Right? This has a well defined answer, even though I didn't give you the path. Right? Even though I didn't give you the path. Okay? This is the z cube by 3. Okay? Huh? From what? 1 plus iota to 1? 2 plus iota, and then you put in limits and just compute, do algebra with complex number. Okay?
Yes, sir.
So the integrals of analytic functions, okay, right? They do not depend on what path you are considering between 2 points, between your limits z1 and z2. Okay?
Yes, sir.
Have you ever heard this integral being path independent? Not in complex numbers, but somewhere else. Some integral being path independent. Work, exactly. Work done. Right? So this work done due to what kind of thing? Work done due to what kind of forces is path independent? Conservative forces. Right? So work done due to conservative forces is path independent. Okay? It does not depend on path. So this is similar to that. Not even similar. It's exactly the same way. It's path independent. Okay? Huh? And what is the specialty of conservative forces? These are forces what? Which come from a potential. These are forces which come from a potential. So force is equal to minus du by dx. U is my potential of the force. For example, coulombs, for example, electrostatic force. Okay? Electrostatic force, this comes from potential. Okay? So this is how these things connect to physics, right? Huh? Good. So now we learned that what did I mess up something?
I think so. We made the integral wrong from -1 to iota.
Oh, okay. This is z square by 2, right?
-1. Last one.
This one.
minus lower limit. Minus 1.
Which one? Minus 1?
Yes, sir. Minus 1 minus 1.
Minus scale. Oh, yeah. Okay, sorry. Oh, indeed. Thank you so much. Yeah, okay. I have scale -1, then I -1, then it's -1. Okay. Good. Thanks for pointing it out. Yeah. Okay. Good. So you can do this integral also. Okay. So whenever you are doing integral of this kind, okay, you should ask about a path only when what you find that okay there is some non-analytic stuff somewhere. Okay, right? As long as you see the function is analytic, you can just do it as if you are doing real fields, real functions. Okay. Now let's move on. Okay. So now since we showed that if a function is analytic in a domain, and where should it be analytic? It should be analytic everywhere, right? Right? Okay?
Yes.
It should be analytic everywhere. Huh?
Yes, sir.
Okay? But at least it should be analytic, even if it's not analytic everywhere, okay? Let's say I have a function which is not analytic here, let's say at the origin. Okay? For some reason, we'll shortly learn for what reason, okay? But let's say I'm just considering these 2 points. Okay? Fine. And if I consider these 2 loops, everything still works. All my proof still goes.
Yes, sir.
Right? Because when we checked Cauchy-Riemann, where did we check? The region bounded by the loop. Right? Which is fine, right? Because your non-analytic stuff is happening here. Right? So this guy would still have a well-defined answer. Okay? But there is a subtlety which I will come to later. right? Because I can consider, because obviously I can show this is same as this, integral over this thing is 0, right? But how about this? How about this guy? Right? So this is my P1 and this is P2. How about this guy? Right? Okay, then you can't do this. You can't do this.
It's not analytic.
Because Cauchy-Riemann equation would not hold here. So our proof doesn't work. Right? For one point, it would be 0 everywhere except one point, right? Okay? Huh? Okay. We learn later on how to assign values to these two. But if your function is analytic everywhere, okay, for example z, then you can just forget about everything and just do the integral. Right? As if it was a real. As if it was real. Okay? Okay? In this case, you can still do the integral and forget if it is, you can still do the integral as if it was real, okay? But you have to be careful. One has to be careful. We'll learn about what thing we have to be careful about. Okay? For now, let's just consider a function which has a single, a function just like this, which has a single non-analytic point. A point where it is not analytic. Okay? And the simplest function you can consider is f of z equal to 1. Okay? F of z equal to 1 to z. Okay? It's a very simple function. Okay? Is it analytic? Is this analytic? Huh?
Except at 0.
Well, I told you that it's analytic everywhere except at 0. And why is it? Well, I think the more appropriate question would have been, why is it non-analytic at z equal to 0?
Because it goes infinity, which is
It goes to infinity, okay? It goes to infinity. In fact, the function is not even defined for z equal to 0. It does go to infinity, right? But infinity is not a real number. Right? So it doesn't take a real value. So if I think of this as a function from complex plane to complex plane, right? How did I define the complex plane? It is x plus iy, such that what? X is real,
y is real.
y is real. So it means if x is infinity or y is infinity, that point is not where? In the complex plane. So this function is in fact not defined for z equal to 0. Right? If you want to define it for z equal to 0, right, you have to add one more number to the complex plane, the infinity. Okay?
Yes.
Okay? When you add one more this infinity guy to the complex plane, okay, you define something called extended complex plane. Okay? This is a set, you can add something to it, right? You can add one more element to that. Okay? You define something called extended. So this is defined for the complex plane. Oh, sorry, it is not defined for the complex plane, but it is defined for the extended. But it still is very singular. Singular in the sense it takes infinite values. Okay? So Cauchy-Riemann and all, they go away. They are not. So it's not analytic at z equal to 0. Okay? That's the only point it's not analytic. The rest, everywhere it's nicely behaving. Right? Gives finite answers. Right? If you check the limits of the derivatives, means ux, you do derivatives, right? Ux, vy, those limits, if you check, like if you reach a point from this way to this way. Yeah, no, but this derivative should also be well defined, right? If you approach from this way and that way, it should be the same, right? So ux, what is the criteria for existence of this derivative, right? If you approach, no. So left hand limit should be same, right? Or this function. This should be continuous, yeah. The derivative should be continuous, yeah, not the function. Okay. Well, the function has to be continuous. Yeah. The function also has to be continuous because otherwise this derivative will blow up. Right? If it has a sudden jump. Good. So everywhere else this is well behaved, everything is nice. Okay. So it's analytic everywhere. Okay. Cauchy-Riemann conditions will hold. Will they? Except at z equal to 0, fine. But what about other points? I didn't check. How do I know Cauchy-Riemann conditions will hold? There is no z conjugate, right? But let's check. Okay. So this is just 1 divided by x plus r to y, which is just what? X minus r to y divided by what? X squared plus y squared. Okay. I just rationalize. Is this fine? So what is this is x divided by x square plus y square minus iota y divided by x square plus y square. Okay, is this fine? Is this fine? Yeah? Okay. What is u? U is this guy. So what is ux? The derivative with x. What is that guy? It is 1 divided by x square plus y square. Okay? Minus x divided by x square plus y square whole square times 2x. So this is what? X square plus y square minus 2x square divided by x square plus y square. Okay? Is this clear? Whole square. So this is what one of them will go. So this is y square minus x square divided by. Okay. Now what is the other thing we should check? Vy. No, that is
Whole divided by x square plus y square.
no. This is fine. Yeah, this is also fine. So what is u1? It is minus 1 over x square plus y square. I'm using product rule. First differentiate this, then plus
2y
x square plus y square plus whole square times what? 2y and then become 2y square. Okay? Huh? And what is this guy? It is minus x square minus y square divided by x square plus y square the whole square plus 2y square. What do I get? Y square minus x square divided by x square plus y square. Okay? Is the same? Is ux same as vy? Indeed it says, except at z equals 0 means the point where x and y both become 0. Right? That's the origin. There they blow up. So ux is vy. What else do we check? Vy. So uy is what? Minus vx. Correct? Which you guys can check at home and it will come out to be zero. Okay? So this function 1 by z. It is what? It is what? Analytic. It is analytic. So now what we are planning to do? Integrate this function. Okay? Over a loop. Okay?
Yes, sir.
Let's first integrate this function over a loop which does not contain 0. So some loop here. What do I get? What do I get? Integral. So let's say this is C1, the loop 1. C1 dz 1 by z. What do I get? What do I get? The point which is not analytic is here. What do I get? 0. Right? Once again, we will use the same. We decompose into x and y, real and imaginary parts, then use what? You use the Green's law. Okay? And you will tell me that if Cauchy-Riemann equations hold inside everywhere, inside this loop, then this integral is 0, which is indeed true, right? We check.
Yes.
Yes, huh? But why did we choose this function? Because of this, right? So we should choose a loop which contains this. Otherwise, we are just doing the same thing. Let's take a loop which contains my point, which is not where the function is not analytic. Okay, which is z equals 0. Okay. Now I can take a complicated loop. Okay. So clearly this integral may not be 0. Okay. It may be 0. It could be, right? It's possible that it's still 0. I don't know. But like in general, it may not be 0. It is not 0. Okay. Now, what is the simplest possible loop I can take? Huh? Yeah. Circle. Huh? I'll do for simple loop. Why do I need to make my life complicated? Let's just do simple loop and see what answer we get. Let's take a circle. What should I keep the radius? What should I keep with this radius? Keep the radius? Huh? Unitary. Yeah. Let's take radius to be 1. Okay, let's take radius to be r. Right? It doesn't really matter. So what is every point on the loop satisfying? what is every point on the loop? How can I represent it? R e power I theta. No? R is the modulus of the complex number on it, and theta is sum. And how do you trace out the loop? You vary theta from 0 to
2 pi.
2 pi. Okay. Now let's do integral dz. Okay? Huh?
Yes, sir.
Integral dz 1 by z. This is. Huh? Right?
Yes.
I don't know how to do this integral. Where should I go? I should go to real and imaginary parts. Okay? But this time I'll use polar form. It's simpler.
Yes, sir.
Okay? Huh?
Alright.
And dz, and this is over what? This is over this loop. C. C is a circle. Okay, let me write CIR circle. Okay? And sorry, what is z over? Right?
Sir?
What is this integral over? This circle, right?
Yes.
On what is every point on the circle?
It's or
E power I theta, right? So instead of doing an integral over z, I can change it to what? Integral over. How do you trace out the loop? Theta, by changing theta. I can change it to an integral over theta because I trace out the loop.
Yes.
Then automatically then sum the function, sum whatever I have sum is. Okay? Okay, good. So now, so this means I have to get dz. It means everything here I have to be replaced by something which is a function of theta. Right? I know z would be what? R e power I theta. Right? So what is dz? Obviously r is constant, right? What is this? R iota e power I theta over d theta. Okay. This is fine, right?
Yes, sir.
Huh? ये ठीक है ना?
Yes, sir.
Okay, good. Now let's substitute it back. Now integral over the circle, okay? This has implicitly limits in it of theta. What should I vary theta from where to where so as to trace out the loop?
0 to 2 pi.
0 to 2 pi, excellent. So 0 to 2 pi. Right?
Yes, sir.
And what is dz? It's r
Capital E.
e power I theta dt. And 1 divided, what is that? E power I theta. Okay? What cancels?
Oh, yeah,
This cancels, right?
I
I can take outside. And what do I get?
2 pi.
2 pi.
Right, 2 pi.
So integral over the circle dz. Right? Sorry, dz.
1 by 0.
1 is what? 2 pi. Okay. So I was able to integrate this function on a circle. Okay, and what do I get? 2 pi. Right?
Yes, sir.
But let's go back to our proof for analytic functions. Why were they 0? Because CR equation were true everywhere. So I can do the same thing here, apply Green's theorem, right? Write real and imaginary parts dz as dx plus iota dy and use the Green's theorem.
Yes, sir.
Right? Huh? And then I would have to integrate where? Inside.
Yes,
Inside.
Right? But inside, so remember those. Let me get back. Yeah.
Use line integrals.
Yeah, see, those line integrals, they became area integrals, right?
Yes, sir.
With what in the argument? The Cauchy-Riemann equations, right?
Yes, sir.
Right? That was if you take Cauchy-Riemann equations on the one side, the LHS of the Cauchy-Riemann equations, right? If you take everything on one side,
Yes, sir.
okay, this is minus Vx Uy. Okay. But then these were 0, right, for analytic functions.
Yes, sir.
Here, they will be 0 everywhere
Except
except at
1 point.
at one point, right? So when you're doing this area integral, right, you're finding 0 everywhere. On every point, you're finding 0 here, 0 here, 0 here, except where? Here. Huh? And the integral is finite, right? So where should this contribution come from?
Is it points?
Right? See, there are two ways to do this integral. One is what we did, 2 pi r. Another is I just use the Green's theorem and all. Okay? But that tells me that you have to integrate dx dy something plus iota integral dx dy some other thing. Okay? That thing that we had above. But this was not the region over this region.
Circle.
Over the circle region.
Yes,
anywhere except at the origin. Right? So this guy vanishes everywhere, the thing in the brackets, right? Because Cauchy-Riemann equations hold. Except where?
At this point.
At the origin. So that's the only point where you will get something non-zero. Right? Huh?
Yes, sir.
And I computed this integral already. The total answer is 2 pi I. Okay? So where should this contribution come from?
You have this point. Imaginary part.
Which imaginary part?
You see points.
Exactly. Should come from this point. This has to be contribution from this point. See, this makes sense if you think this way. This integral is independent of the radius of the circle you chose.
Yes, sir.
It didn't depend on the radius, right? You got 2 pi I, even if your radius was capital R, it could be anything. Right? So if you make this R smaller, your integral will still not change. Right? It will still 2 pi I.
Yes, sir.
Right? So it means these points, when you make R smaller, let's say you take, if you have taken R to be like this, something smaller, okay? Right? You have now shrunk this region of integration. Right? So it means these points are not even contributing. Right?
Yes, sir.
Because if you integrate over this big region, right, if you integrate this way, if you integrate over the big region, if you integrate the smaller region, it's same. So it means these points are not contributing, which is indeed true because these brackets vanish because of Cauchy-Riemann equation. Right?
Yes, sir.
Okay? So it means whatever contribution you're getting, it has to be from the origin. Okay? Huh?
Yes, sir.
Okay. Yes. Good. So you see the points of non-analyticity, the points where the function is non-analytic contribute to the integral. Okay? The other points won't contribute in this region when you do integration this way. Okay? Did you get it?
Yes.
Did I mess up something?
No, sir.
Huh? Everything's okay?
Okay.
This is a very important integral. This integral that is done. This is a very important integral. Okay? Huh? And you learn with time. Okay? With time you learn that if I have any complex function, okay? Huh? If I have any complex function and I am integrating it over some loop, okay? Huh? It is basically the same thing, some number times the same thing, 2 pi times the same integral. Okay? This is just a sneak peek of what eventually I have to teach. Okay? Huh? So that's why this is to stress the importance of this integral. Right? But we just showed this integral is equal to pi for just what? A circle. No, for just one loop circle. Right? Huh? What if I had taken something else? Okay? Let's try to figure out, does my answer change? Okay? So now I take some loop, some weird looking loop. The non-analyticity is here. Function is non-analytic here. Okay? Okay, good. So I want to know what is the integral. Integral, let's call this C dz times 1. I want to know this guy. Okay?
Yes, sir.
Hmm? Okay. Huh? Fine. Okay?
Yes, sir.
Let me not, for a while, let me not think about this loop. Okay? Huh? Just for a while. Let's say if my non-analyticity is here, right? If I consider a loop like this, so this is some weird curve, this guy, but then there are two perfectly straight lines, okay, and then there is a good perfect circle, okay? Huh? What would be the integral? Huh? 0. Why? Because analytic everywhere inside, right? This is outside. Okay? Good. Huh? Huh? What if I slowly move these lines like this? What do I get? So I now consider a loop like this. L1 is in here. I consider a loop like this. A line like this. Okay? And the line arbitrarily close to this. It's so close that they are almost on top of each other. Okay? I have just drawn them away from each other. Okay, so that you can just visualize the loop. Okay. And then there is a perfect circle. Okay? And then outside there is some weird shape. What is this integral? 0. Right? Still 0. It's the same loop. Well, not the same loop. It's like the idea is same. It's we have to take the region inside which does not contain. Huh? Okay. Huh? But now let's think about, so integral over this loop, let's say I call this loop as L. This full loop is L. There are many parts to this. Right? What? The circle. Right? The circle CIR. This line, right? L1, small l1. This weird curve C1. Right? This weird curve. And when you come back,
L2, C2.
Now integral over L dz 1 by z is what?
0.
To 0. Right? Why? Because you have to look at the analyticity inside there, which is Cauchy-Riemann equations everywhere. Right? 1 by z is analytic inside. But I can split this loop and do the integral partwise. So this guy is same as integral over the circle, right? Integral over the circle. Let's say I am going this way. No, I am going the other way. Integral over the circle, right? This way. Okay. Huh? So first I take the integral over the circle, then what?
Integral over the circle.
Line L1. Huh?
Yes, sir.
dz by z. Then
L2. Yeah.
L2.
C1.
Right? And then what?
C1.
Then what? C1. But this sum has to be 0. If I add all this, I should get 0, right? Because the sum of these integrals is just the total integral over the big loop. Okay?
Yes, sir.
What about integral L1 plus integral L2? What about that? Remember, L1 and L2 are two lines who are like almost, they are on top of each other. Okay? What?
Opposite.
They should what?
Equal.
Equal and opposite. They should what? Cancel each other. Right?
Yes, sir.
They should cancel each other. Right? It's like it going from you said this just a few minutes ago. Well, not a few minutes ago, but some time ago. Remember when we did this P2?
P3 goes to this.
You said P3 was the reverse, exact reverse of this. Yeah? You said so yourself that this is 0. Why? Because they are negatives of each other. So if I go back to the stuff that I was doing, okay, integral L1 and L2, they cancel each other, right? Because these lines are on top of each other, right? Okay. Well, not really on top of each other in principle, because if they are on top of each other, that might cause problems, right?
Yes, sir. There is no.
Yeah. And so we make them infinitesimally close to each other, these L1 and L2, so that essentially they cancel out.
Yes, sir.
Yeah? But you can take them, you can think of them on top of each other, it's okay. As long as you remember this circle. Okay?
Yes, sir.
Maybe it should be okay. But I have to think of it carefully, right? Yeah? But for now the idea is clear, right? They are infinitesimally close to each other and they cancel each other.
Yes, sir.
Okay. So integral L1 and integral L2 they cancel. Okay. So what do I get? Integral over the circle dz by z
is equal to
is equal to minus times integral over c1 dz by z. Okay. But c1 which way I am going? So circle I am going this way and then I go this way. I am going what way? Opposite to what I am doing circle. Right?
yes,
So can I change c1 to minus c1?
yes, sir.
Right? So this should be same as integral over c, where c is the loop, but I am going clockwise. Right? Okay. Once again, same idea. The thing that you use. So integral over the circle dz by z. If you are doing clockwise, this integral over this loop dz by z. Right? Huh? Provided you go clockwise on both. Otherwise, there is a negative sign. Otherwise, there is a negative sign. Huh? So I can. Okay, contact. Okay. Huh?
Yes.
So I can just drop this L1 and L2, right? Because they cancel. Huh? I hope this works. Yeah, it does. Good. And then there is this weird curve, but I have to go clockwise, same direction.
Yes.
Then integral over the circle is same as integral over this loop. Okay? Right? Huh? Did we assume anything about this loop? We didn't. What were we able to show? We were able to show that integral over this thing is same as integral over circle. But integral over the circle we know. 2 pi I. Right? So this thing that I wrote in box, I can just replace that as a more general statement. Integral over any closed loop, but which contains what? Origin. The origin should be there, otherwise the integral is 0. Right? Because analytic inside.
Yes, sir.
Right? Integral over any closed loop C dz by z is what? 2 pi. Okay? Huh?
Yes.
Is this fine? Right? So this result that we derived, we did it for circle, right?
Yes.
But circle is not necessary. I mean, you could have chosen any shape you want. The reason we did it for circle, it was very simple to do the integral. Right? It will be very difficult to do the integral on some very complicated loop. Right? But you know the final answer. Right? Huh? So we did it on a circle and we were able to show that what?
This is same as.
That it doesn't matter. You can deform the circle if you wish. Right? Huh? There is only one thing you are not allowed to do. You are not allowed to deform the circle such that the origin leaves out. Right? So this is, I can think of this as deforming the circle, right? I can deform the circle here and there and it gets me this. Right? Huh? So you are allowed to deform your curves on which you are integrating. But you are
Not allowed to define that point which is not.
You are not exactly, yeah, good general statement. So you are allowed to deform the circle. You are allowed to deform your curve on which you are integrating the closed curve, right? As you wish, as you wish. Okay, but you are not allowed to take a non-analytic point outside. If it was inside, you have to keep it inside. If you take it outside, then the value of the integral will change. You can see here, if I deform this circle, okay, if I take this part of the circle and move it like this, so basically I deform the circle like this, right? The integral value changes, it becomes 0. Okay, because this is the point in dz equal to 1 by z, if f of z equal to 1 by z, that contributes. Huh?
Yes.
Okay. Huh? So a bit more general statement. Earlier what we saw, that no matter what closed loop you consider, the integral is 0. Integral of the analytic function is 0. Okay? This theorem is called something, I don't remember. It's called integral theorem, maybe. Yeah, I will like to know what is it called. Okay? But, so earlier what you saw, that if my function was analytic everywhere, there was no point where the function was not analytic. Okay? Huh? Then I can deform my curves wherever I want. The integral will always be 0. It doesn't really matter. Right? Any curve you consider, function is analytic inside the curve. Yeah. But when you have a non-analytic point, you can still deform your curve, right? But make sure you don't include any. You don't include any what? Non-analytic points. Sorry, you don't exclude any non-include. Basically, जितने भी non-analytic points इसमें है, उतने ही रहने चाहिए. इधर एक था, उतने ही रहने चाहिए. तब तक integral same रहेगा. The moment you include a non-analytic point, an extra non-analytic point, okay, or you exclude an extra non-analytic point, okay, the value of the integral changes. Okay, is this clear?
Yes, sir.
Huh? We'll learn more. Okay. For now, just focus on integral, okay, of dz by integral dz by z over any closed curve or any closed curve which contains what? Origin. Okay. Why is origin special? Because that is the point where the function is non-analytic. It's just 2 pi. It's just
2 pi I.
2 pi. Okay. So just because there is a non-analytic point, okay, that doesn't mean that this will always be non-zero. It could sometimes be 0, even though there is a non-analytic point. Okay? I'll give you an example. Okay, that's the last thing we'll do today. And we'll stop. Okay? How about integrating over some curve, over some not curve, over some loop, okay, over some simple loop, dz by z, dz by z, z to the power, let's say z square, we'll generalize it a bit later, let's do dz by z square, okay, so integral over some curve, right? Now, what curve should I take so that my life is simpler? What curve should I take? Oh, what loop? Sorry, I keep using curve. What loop should I take? Huh? Circular, right? Why don't you reply fast? And the answer is obvious, right? Circular, right? So let's consider a circle of some radius r. Once again, it's the same thing. Z is r equal I theta. Theta varies from 0 to 2 pi to trace out the curve.
Yes, sir.
Loop or curve here. Okay, then what do I get? Over the circle. Or now I am changing the integral to circle. Okay? Now this is iota e power I theta e theta divided by what? Z square, that is iota square e power, okay, that is r. But yeah, divided by e to the power what? 2 iota theta. And then I get r square. Okay? Huh? Right? What do we get? And theta goes from 0 to 2 pi. And what do I get? Iota 1 iota goes, and I'll get e power minus I theta d theta 0 to 2 pi. Is this okay? Huh? What is this guy? Integral 0 to 2 pi e power minus I theta d theta. What is this guy? Huh? What is it equal to? Huh? Yeah, it's 0. Right? If you integrate it, just integrate it at home. Okay? Huh? Integrate it at home and you'll find this is 0. The answer is simple. E power I theta integrated gives you back e power I theta. Then when you put a limit, when you put e power I 2 pi and e power 0, you get the same answer. Right? It's the same. And then when you subtract it, it vanishes. E power I 2 pi, e power minus e power 0 is a 0. Right? Both are 1. So this is 0. Right? But the function is not analytic at z equals 0, right? The function we have is 1 by z square. Right? Non-analytic at z equals 0 because it blows up infinity. It's not well-being. Right? Okay? So just because you have a non-analytic point, that doesn't mean that the loop integral will always be non-zero. In general, it may be non-zero. It is non-zero, right? But it could be 0. We learn when we do more that what exactly determines whether this is 0 or not. Okay? Huh? Okay? But for now, these integrals are very crucial. Okay? You will see I can reduce any complex function to integrating 1 by z, 1 by z square. Okay? Huh? What about something else? What about integral over the circle? Ah, okay, one second. So I can write down this result. Circle dz z square equal to this guy is it. Okay? Huh? But once again, I can use the same argument, right? This argument that I used to use for the circle. This guy. Right? Same argument to show what? That it's not true for the circle only. It's true for any closed loop. Right? It's true for any closed loop. Same argument, right? In this argument, there was nothing which says that I was integrating 1 by z. It could have been 1 by z square and everything will follow through. Right? Why did you integrate clockwise both? Right? So can I instead of writing this integral on circle, can I just write integral over some c? Right? So integral dz divided by z square is 0. Right? Always. Whether you enclose the origin and you don't enclose the origin, it doesn't really matter. Okay? What about 1 by z cube? What do I get? Huh? So you have to do same business again, but with what? Z cube now. Right? You will see you get 0 again. Z cube, you will have 3 iota here. 3 iota. E power 2 i theta. Once again the same thing. E power 4, whatever. E power 4 pi minus e power 0. That's 0. What about z to the power 4? 1 by z to the power 4. Huh? What about 1 by z? Same thing, right? Z plus 4, 0. Right? So integral. What about integral 1 divided by z to the power n? For any value of n. 0. Always. Even though the function is what? Non-analytic way at origin. So, integral, so can I write it? Integral of some closed loop dz by z to the power n is 0, right? Except when n is what? 1. So, this is 2 pi I delta n comma 1. Where n delta n comma 1 is what? Chronicle delta. Excellent. Chronicle delta. So when this n is 1, this chronicle delta hits, it's 1. So I get 2 pi I. But when n is anything else, 3, 4, whatever, it is 0. Okay? But what if n is minus 5? What if n is negative? Let's say, what if n is minus 5? Okay, this equation, okay, I just wrote this equation down. As per this equation, it should still be 0. Right? So n equal to minus 5 is 1 by z to the power minus 5 dz, which is my integral z to the power 5 dz. This is even simpler, right? This is 0. Why? It's analytic. Yeah, there is no certainty of z equal to 0. Right? There is no, you actually extra issue. There is no certainty of z equal to 0. Right? It's a 0 because it's analytic. Right? Everywhere. So by definition, any closed loop you take. Right? So remember, I'll later on qualify what do I mean by simple closed loop. For now, just let your intuition guide you. Right? Closed loop, just simple closed, just take loop. Bas. Right? Not loops like this. Not loops like this. Okay? Closed loop, something which is simple. Right? But we'll qualify it later on. Okay? Okay? Huh?
Okay.
Fine. So shall I print down the final result? Okay, I'll already print it down. Integral over any closed loop dz divided by z to the power n is 0 except when n is 1. Then if the loop contains origin, then it's 2 pi, otherwise it's 0. Okay? This is the take home message of today's class. Okay? Okay? Everything clear? Any questions?
No, sir.
Huh?
No, sir.
Yeah, so you understood everything, huh?
Yes.
Huh? Good. See you tomorrow.